Hi, this is Roger Green, host of the Surfing the NASH Tsunami podcast. We are offering 3 separate conversations from Wednesday night's episode, 14-variable machine learning model identifies probable NASH patients from electronic health records, hardly our shortest or most concise title to date. At any rate, in this conversation, Jörn Schattenberg, final author on the Journal of the American Medical Informatics Association paper announcing the NASHmap model, discusses the motivation that led his collaborators and him to develop a model to predict probable NASH patients based on EHR data, and describes the work that went into producing the model. Chris Cowdley, Louise Campbell, and I asked questions about the project. NASHmap is a special tool, the leading edge of our future. You'll want to know about it. So sit back, listen, enjoy, learn, and when you're done, join the discussion on our LinkedIn and Facebook discussion groups.
Every week, a global community of fatty liver disease stakeholders comes together to explore the most important challenges in diagnosing, treating, and developing medications for patients with fatty liver diseases. Join hepatology researcher and key opinion leader Professor Jörn Schattenberg, liver wellness advocate Louise Campbell, pricing and forecasting guru Roger Green, and this week's guest, hepatology researcher and key opinion leader Dr. Chris Cowdley, as they discuss Professor Schattenberg's recent paper on machine learning and NASH diagnosis this week on the Surfing the NASH Tsunami podcast.
By now, if you've been with us for a while, you know that most of the leading key opinion leaders, and certainly the folks who are good enough to come on Surfing NASH, each has several principal areas of research. And today, Jörn will be talking about one of his that I don't think we've brought up yet, machine learning for the purposes of prediction. Jörn's been speaking and publishing on this issue for several years. Last month, the Journal of the American Medical Informatics Association published a paper on which he was last author titled Development of a Novel Machine Learning Model to Predict Presence of Non-Alcoholic Steatohepatitis. It presents the NASHmap model, which is unique for reasons Jörn will explain as he discusses the paper. So Jörn, first, just congratulations to you and your colleagues. What a great piece of work.
Thank you, Roger, and thank you for giving me the opportunity to discuss it online here with you and really break it down, what it could mean in terms of patient identification. It's an interesting approach and a research that I stumbled in by chance, but I guess today the technology advancement is such an omnipresent situation that it's just at the top of your head, or it's something that you'll end up thinking, how can I apply these powerful machine learning techniques, artificial intelligence, to solve a problem in clinical practice? And I'll just go right on and dig in and say that from my perspective, one of the major issues in the field, and I highlighted that I talked to medical professionals and that it was up in newspapers still, this disease being highly prevalent is not well recognized. And many clinicians are missing the disease. And also from a sponsor's perspective, if sponsors come to me and say, where do you find your patients? How can we identify patients? There is still a lot of unmet need. Coming from that angle, the group of collaborators got together and asked the question, how can we improve patient identification? And the way it was done here in this paper, and this is pretty much the development of the analytical tool, the machine learning algorithm, as you like. It has some clinical data in it, but hopefully there will be a publication that details the entire clinical aspects in a little bit more depth. But looking at how the model was developed, the unique thing is it took 2 big databases available in the US. One is the NIDDK, National Database on Diabetes and Kidney Diseases, and it's a longitudinal registry that actually contains liver histology and patients characterized with liver histology. It has a lot of additional data points, and it has an in-depth information that you can actually exclude other liver diseases and really come up with a NASH cohort. The second database we used in the end after developing the model to train it and validate it is the Optum electronic healthcare record database, again, which is a large adult patient database in the US, which most of you are comfortable with. And it contains just a tremendous amount of data. And the way the paper is built up and the way we followed our research questions, that we took the NIDDK model first and built a machine learning model by selecting individual features from within the NIDDK database to then predict the outcome of a patient having NASH versus not having NASH. This is at the heart of the model. And I'll give you a little bit more insight, but maybe stop here for a second because I've been talking a lot, and just following up, we can decide whether this is the right question to be asked or maybe something that you'd like to feedback at this point.
Yeah, so Jörn, congratulations on this really important study. What I really liked about the study was that you had a training set and a validation set in both cohorts. And obviously, we will know that the NIDDK cohort is much more likely to be enriched with patients with NASH and probably more carefully phenotyped since it comes from the National Institute of Digestive Diabetes and Kidney Disease, where they're experts, whereas the other population health database would be more likely to have a more heterogeneous population. One question I had was, it looked like when you identify the patients that had a diagnosis of NASH but also had a liver biopsy in the Optum database, they were much fewer than the patients who had a diagnosis of NASH but not a biopsy. Can you expand a little on that and how you think that might have either weakened your findings or maybe made it more generalizable to the broader population?
Yeah, that's a very important point in it, and it goes into how the validation set was then used to explore the algorithm. Optum has something like 15 million records we were able to access, and we didn't discuss how we built the score yet. However, it's based in its most commonly used form on 14 variables that it needs. So we had 3 million data sets in the larger Optum electronic healthcare records with those 14 features available, and actually 70,000 patients with an ICD-10 code of NASH. Within those NASH-coded ones, it was 23,000 that had those 14 features, but only 1,000 with liver histology. So it's a 23-fold difference, as you highlighted, patients that do actually have a biopsy in Optum compared to the coding of NASH. I think it's something we do see in database research very frequently. While there is a strong undercoding likely to occur, those patients that are coded are more phenotypically likely to have NASH, in my personal experience. And then a very small subset actually went on to get biopsy. How did that influence the results? I didn't give you too much details in the test accuracy quite yet, but I can say that they were actually very similar between the NIDDK with a very well phenotyped cohort and the Optum electronic healthcare records, which with an AUC of 0.82 in the NIDDK and 0.79 in Optum. And that told us that despite all gray areas that are there in Optum, that algorithm that was built in the NIDDK was pretty robust. And at the end of the day, actually applying the 14-feature model to the large Optum electronic healthcare records, we identified an additional 900,000 patients with probable NASH that are not coded compared to the 23,000 that are actually coded. This is where the power of the algorithm then comes in. You have large databases or, let's say, electronic medical records, and you can run that data, you can run the algorithm and identify patients with probable NASH. One very important point here, it's not diagnosing NASH, and I think Chris would have asked that in a follow-up question. Of course, I don't know that the patient has NASH, but it's a patient that has a very high pretest probability, so it's an enrichment tool that you will need to then guide on additional diagnostics and potentially follow-up.
My one follow-up question is, I think based on this, you have a 1 out of 20 patients in whom you suspected NASH actually had a biopsy, but on the other hand, the characteristics of the 19 out of the 20 that did not have a biopsy was very similar to the 1 out of 20 that had a biopsy. And you can look at it and say, well, that's a limitation or a weakness of the data set, but you can also look at it and say, in the real world, it's very likely that biopsies are going to be done in a minority of patients who likely have NASH. To me, it makes the data more robust and in some way more applicable to the general population, in that the presence or absence of a liver biopsy did not necessarily change performance characteristics of identifying likely NASH.
Absolutely, that's correct, and I agree that it tells us that the AOC between those two data sets is not particularly different, and I do see, as you highlighted, that again many people will fortunately not need a liver biopsy and still have NASH, so that's where the algorithm can help us. And going back and starting out, the machine learning algorithm we call called NASHmap was developed in the NIDDK with 704 patients that had histologically confirmed NASH, respectively histologically confirmed non-NASH. And it was split in a training and a testing set 2-to-1. And what the machine does is it takes all available data points and knows the outcome. So it compares the NASH versus the non-NASH case. This was a decision tree building model, and it takes one variable, splits all the NASH versus the non-NASH cases, and then adds an additional variable to separate them more precisely. Now, when I looked at how the model was actually built and how it separates cases, the first thing that struck me is that it doesn't take cutoffs that I would usually consider clinically relevant in clinics. For example, the top feature that came out in the model was HbA1c, but it didn't split all patients according to an HbA1c of 6.5 and higher, indicating of type 2 diabetes, or lower. It took a cutoff of 8.2 at one point, and then it ran additional features underneath that in the same tree, and it looked at AST and ALT and used different cutoffs to separate those. Now, this is one tree that was built. That data set was then again entered into a second tree where the algorithm again split the cases NASH and non-NASH and used those parameters to separate them. In that second tree, they could actually use a different cutoff of HbA1c again. This is where the strength of the machine learning model came in, that it's capable to separate individual numbers to a much higher extent to dissect patients with NASH and non-NASH than a clinician would be able to. And most of the time, I probably use 5 or 6 phenotypic features, including transaminases, obesity, type 2 diabetes, to say this patient has probable NASH. We're probably not too bad with some experience with that, but again, the machine learning model is available to then non-expert and outside of specialists' offices, and I think this is the real advantage where it kicks in with a potential. We've used those 14 feature model to predict, and again in the training set, the AOC, I think I mentioned that was 0.82, and separating those NASH from non-NASH cases. To be able to use a slightly slimmed down data set, we also developed the 5 feature model. This can be important if you have data sets that do not have all these features available. Please go visit the paper to get all 14 of them. But for the 5 features, I'd like to say it's HbA1c, AST, ALT, interestingly, total protein, and triglycerides. And I think with these 2 models, which most databases have, or electronic medical records, you're able to apply this tool and actually enrich your population, identify unidentified patients, or in large data set do research with this.
We hope you've enjoyed this recording. If you have any questions or comments about the content of this conversation or the entire episode, please send an email to questions@surfingnash.com. We are releasing 2 other conversations from this episode. Please join the discussion on our LinkedIn and Facebook discussion group to talk more or ask questions. Next week, we will post daily episodes Wednesday and Thursday evenings from the 4th Global NASH Congress, and we'll be back on our regular schedule the following week. I hope you'll join us next week for the NASH Congress. Until then, stay safe, surf on, see you on the podcast. Bye-bye now.